Hello everybody! In today's video lecture, you'll learn about simple projectile motion. If we launch an object from a certain height with only a horizontal velocity, then the object will travel along a parabolic trajectory, like the person shown in this picture. We call this motion simple projectile motion. At the end of this lecture, you will be able to answer questions like how far out will he land? But first, let's consider how long will he stay in air. Do you think he would have landed sooner or later if he ran a little faster? To answer, check out the following demonstration with two billiard balls, where one ball is simply dropped and another is kicked horizontally at the same time. Which do you think will land first? Well, which one landed first? Let's take a look at this picture of a similar event. Using the horizontal guidelines, can you tell which ball is closer to the ground at all times? Both fall the same vertical distance in the same time. The vertical distance fallen has nothing to do with the horizontal component of the motion. Therefore, the vertical component of a projectile's velocity is just like the motion for a freely falling object. Let's take a look at the horizontal component of the motion. Look at the spacing between these vertical lines. What do they show? Well, this ball moves equal distances at equal times horizontally. The ball's horizontal component of motion remains constant. Why is that? Because gravity acts only downward, not sideways. Therefore, there is no net force to change the horizontal motion of the object. Horizontal acceleration remains zero. The horizontal component of motion for a projectile is just like the horizontal motion of a ball rolling freely along a level surface without friction. Therefore, the horizontal and the vertical component of a projectile motion is completely independent of each other. Suppose you have a tennis ball and you dropped it from an 80-meter cliff. Can you figure out where the ball will be at every second? Sure you can, it is free falling. Remember the displacement equation. Delta x is equal to v original t plus 1/2 at squared. Let's modify it for free fall. We will use delta y for it falls along the y-axis. V original y, because it has only y component of velocity, and let's not forget t, plus, and remember the acceleration is going to be constant and it would be g, and since the acceleration is downward only, we are going to use negative. So we are going to go negative 1/2 g t squared. Now, since the ball is just dropped, this component is just going to cancel out and we are going to have simply delta y equal to negative 1/2 g t squared. Now, calculating the position of the ball for every second is quite easy now. All I have to do is plug in the values. So for first second, delta y for 1 second is going to be negative 5. 1 squared is going to be negative 5 meter. Now let's use this ruler to mark the position of the ball, and let's use the scale of 1 centimeter equal to 5 meter. So if I go 1 centimeter down, it will correspond to 5 meters down. So the ball would be right here. For 2 seconds, delta y2, all I have to do is replace the time value. Negative 5 times 2 squared is going to give me negative 20 meters. So it is going to fall 20 meters and it's going to correspond to 4 centimeters here. And next, the 3 seconds is going to be negative 5, 3 squared is going to give me negative 45, and 45 corresponds with 9 centimeters. 5 times 9 is 45 after all. And delta y 4 seconds is negative 5 times 4 squared gives me negative 80 meter. So the ball is going to be at the ground, 16 centimeters right here. Well, this is if it's just free falling. Now, what if you are just rolling this ball instead of dropping it? You are just rolling it on a frictionless surface with an original horizontal speed, the original x is, let's say 10 meters per second. Now, and this surface is frictionless. If there is no friction and if the ball is rolling, there is nothing to change its motion. Therefore, it is going to make constant motion and is going to travel equal distances at equal times. So every second is going to go at 10, then 20, then 30, then 40 centimeters, so on and so forth. Now, here is the real question. What if you throw this ball horizontally from this cliff? Can you find out where this ball be at every second? Sure thing. All you have to do is combine the horizontal and the vertical components of this motion. Horizontal component is going to stay constant, so we will use the equation for the horizontal component, big X. We will use this equation, delta X is equal to V original X times the time, because it's just constant motion and acceleration along the horizontal is 0. Remember, there is no friction and gravity doesn't act on horizontal. Therefore, there is nothing to change this motion. It does not have any acceleration. This is the only equation we can use to calculate the horizontal position of this ball. Vertical component, however, is going to exhibit free fall. So we are going to use this equation. Delta y is equal to V original y t minus 1/2 g t squared. Well, since we are throwing it horizontally only, this term is going to go to 0. So you can consider it as delta y is equal to negative 1/2 g t squared. So this is the only equation you need to calculate the position along the vertical axis. Now, can you guess what happens? At the end of 1 second, the ball is going to go 10 meters out and 5 meters down. So you can mark its position at right here, 10 meters out, 5 meters down. And combining everything that we know, at the end of 2 seconds, it's going to be 20 meters out and 20 meters down. So it's going to be about here. And next, it's going to be 30 meters out and 45 meters down. So it is going to be approximately here. And at the end of 4 seconds, it is 4 meters out and 80 meters down. So it's going to be about here. And if we combine all these points in a smooth curve, as best I can draw a curve at this point, it is going to look exactly like a half parabola, just like we discussed a simple projectile motion would do. Here is our first example problem. Billy stands on a bridge, kicking stones into the water below. Well, for this type of problem, I strongly encourage you to draw a diagram to begin with. So here is your y and x-axis. So let's see what we know. Billy kicks the stone with a horizontal velocity of 3.5 meters per second. So V original horizontal is 3.5 meters per second. and the stone lands in the water 5.4 meters out. So its delta x is 5.4 meters. So I need to solve for delta y. That's my unknown. Now, what else do I know? I know that for this type of motion, the original y velocity is 0. And there is no acceleration for the horizontal. And the acceleration for the vertical is just gravity, negative g. Okay, now let's remember our equations. We have the big X for the horizontal component, and the equation that goes with it is delta X is equal to V original X times the time. No mixing and matching, you have to use all the X components here. And then for the vertical component, Y, delta Y is equal to V original YT minus 1/2 GT squared. Okay, based on what I know, I think I need to use the X component equation first to calculate time, and then use that time in the vertical component and be done with it. I can see the solution. Okay, so rearranging for time equal to delta X over V original X. So we have 5.4 divided by 3.5. And consulting a calculator, the time seems to be 1.54 seconds. All right, now let's use this time for the vertical part of the motion. So we know that there is no vertical original velocity. So delta y is equal to negative 1/2, 10 for simplicity, and 1.54 squared. So delta y, checking in the calculator, seemed to be 11.86 meter negative. Now, why is delta y negative? Because we decided downward to be negative, right? So, and this motion of the object is downward. So if you want to find this is y final and this is y original, and if you want to solve for y original, that's what you do. Delta y is equal to y minus y original. So negative 11.86 is equal to 0 minus y original. So you see y original is 11.86 meter, positive as you expected. All right, that's the answer. And here is the last question of the video lecture. Oh my, a car is plunging down a cliff. So let's see. X and Y axis here. So it is going to land in 140 meter out and 245 meter down. So delta Y is 245 meters. Now I'm going to try something a little bit different now. Remember how we always take the down direction negative? Now I'm going to take the downward direction as positive. So I'm just going to say this is positive and this is positive. Can it be done? Sure, why not? If I do that, let's see what will be different. Only thing that will be different is delta y won't be negative anymore. Downward direction is positive. Remember, delta y is going to be positive. What else? Ax is still no changes there. And ay is still going to be downward and g. But downward and g is not going to be negative g is going to anymore because downward is positive. So it's going to be positive g. So this means our x equation is still as it used to be. Delta x is equal to v original xt. And our y equation is, remember, delta x v original xt plus 1/2 at squared, modifying for free fall. So I'm going to go delta y equal to v original yt. Now I'm just going to replace acceleration with g, but not negative g, just g, plus 1/2 gt squared, and that will be 0 as usual. Now I need to solve for time first, and I need to use the vertical part of the motion because I know more about that part. So delta y is 245 is equal to 5 t squared, dividing both sides with 5. T squared is equal to 49. So t is equal to 7 seconds. And then going back to the original x is going to be delta x over t. So it is going to be 140 divided by 7. The original x is equal to 20 meter per second. See, it makes no difference if you took downward as positive or upward as positive. It still gives you the same exact answer. So you have a freedom here to choose how to solve this kind of problems.